Hello, I'm Varun, and today I'll be fine-tuning a medical LLM. I will be fine-tuning an LLM to make it a doctor guidance specific LLM. Okay, so I'll be using the Hugging Face data to train it, and uh, and to be specific, I'll be using the supervised fine-tuning on the LLM so that I can train it to give me a relevant answer, just like a doctor, right? So first of all, let's go towards some basics. So let's go towards the basics, that what is LLM, uh, how we can train an LLM, like what are the types of tuning we have, right? So let's see them. So basically, LLM main part is the transformer, right? In the transformer we can see that we have an set of encoders, then we have the set of decoders, and inside we have the encoder, we have feed forward and the self attention, right? And just self attention just give in self attention, when the one word is getting processed, right, then it get attention to other words also, so that it can develop a context, right? And feed forward is just refining the output of the self attention, okay, so that it can give it forward to the decoder side, right? So if we see for if we move forward, then we can see that okay, there is a self attention and it's giving it to feed forward neural network that is giving to the decoder, right? And in decoder we have an extra layer, there is encoder decoder layer, right? So that we can just focus on the relevant parts, right? Relevant parts of the output which our feed forward neural network has given to us, right? The context specific. Okay, after that we can see that let's move forward. So this is basically vector. This is the French word. Okay, three French words are getting converted into vector, then going to the self attention. Then after self attention, it's converting into a Z, which is a Q into K into V to be specific, query into key into value. Then it is getting into the feed forward neural network, right? So this is the logic, right? Then we can see that okay, initially I want to make a context like what it refers to. The animal can't cross the road because it was too tired, right? What is it? So at one time it can just see these five things to make context, right? Okay, now the self attention. If we see the self attention, you can see that okay, there are words like thinking and machine, like two words converted into vectors, right? These vectors are multiplied into the pre-trained matrices, okay, pre-trained matrices, weights, the pre-trained weights. After getting x into wq, it will give me q1, x2 into wq, it will give me q2, x1 into wk give me k1, and similarly x2 into k to wk give me k2, right? This is key, and q into k last will multiply it by value. To be specific, we can give use this formula, right? It makes a formula in the end like softmax q into kt upon d. What is it? Like we have a q into k, right? We got the q, x into wq, right? Q into k, we matrix multiply these two. After that we do the scaling. What is the scaling? The normalization, dividing by the dimensions, right? Dimensions, divided by the dimensions. After that we mask, we do the attention masking here. I'll explain it further in my project. I have done it my fine tuning also, right? So after that there is softmax layer, which converting it into a probability form. After the probability has been multiplied by the b, x into wb, right? After that we'll get our attention. So this is the how the attention is being calculated. If we just make it extend it further, we can see that okay, we have two words, right? Thinking and machines. We have embeddings x1 x2, we have q1 k1 v1, right? Multiplying it by the pre-trained weights, right? wq wk v, right? After that we get a score q into k, q into k, divide, normalize it, reduce the dimensions, right? Divided by under root dk, right? We get the, after that we convert it into probabilities, right? Using the softmax layer. After the probabilities, you can see that okay, when we are doing the softmax probability multiplier, the v and v2, right, x in 1 into wb, right, retained matrix it was divided with, then we get a z1, right. This is the attention we got, right. So this is the formula. We can see q into k divided by dimensions will give you v, and in the end we'll get a z, right. So this is it. Let's move forward towards how we are training, right. So for training concept, you can see that okay, let's see training. So I have to get an example of how ChatGPT is used to train, right. So first of all, there is generative pre-training, which give me a base GPT model. Then we do the supervised fine-tuning it. Then reinforcement learning to human feedback. If we extend it further, we can see that okay, we have a simple generative pre-training, right, GPT. So what if we do, we get the data from internet, we get the data from documents, okay, we feed it to the transformer, then it creates a GPT which will do text summarization, sentiment analysis, sentence completion and translation. But what I was expecting it to do chatting with me, conversation with me. Then what I can do, so it should know how to do conversation, right. So there is a supervised fine tuning, right. uh, so there is a human agent, okay, a person. Then there is another person, uh, to whom, in which we have to convert the agent into, right. So he will give a request, right. They will do chatting with each other, request and response, request and what should be the ideal response, request and what should be the ideal response. After that we make a corpus of that data, right. There is a conversation, then there is ideal next response, there is a conversation history till now, then is an ideal next response according to this conversation history. There is conversation history, then ideal next response. Then after that we give it to the GPT model using stochastic gradient algorithm, and we make our SFT model, supervised fine tuning model, right. So after that we do the reinforcement learning through human feedback. This is involving a human, so that he can rate the rank the responses, right. So the GPT trained till now on the corpus will chat with the human, and after that we get the responses, right, alternate responses a, that okay, he gave response a, response b, response c, response d. Then he will now rank these responses, not directly chat. He will just rank that okay, this response was better than this, and this was better than this, and this was better than this, right. So this is how the scoring is being given. And after that, due to that scoring of that conversation history of scoring, we make a model, right. This is a reward model. And after that, in an environment of chatting where one model is behaving like a person I want to chat with, and behaving like me also, that what response I will be giving, he'll be training itself. And the KL divergence, after the check for a KL divergence, this policy model that getting the reward, giving me the ideal next response, and giving me the request, this model will train itself and it will become a chat GPT model, right. So this is the way how we train chat GPT model, right. In this project I'll be doing this only supervised fine tuning, right. So let's start, right. I have given a basic introduction about the project, right, that what are we going to achieve, right. So rest of the concepts we will study further, right. So first of all we'll be importing Unsloth, right. What is Unsloth? Unsloth is like a power boost to our training, right. So what it do, it enhance the fine tuning, right. So the logic is that okay, LLM takes a lot of memory, right. LLM takes a lot of memory, and the training requires a lot of power and the memory also. For example, it's like a big machine, right. In a factory you get a big machine, it requires a lot of power, right, and it requires a lot of space because it's a big machine. LLM is that big machine. So what it do is, it just give it just make that machine enhanced so that it takes less space and it get trained fast on new data, right? So for that we need we need PEFT, in which we'll be doing QLORA and LORA, right? Low rank adaptation and quantized low rank adaptation, right? So that thing will be done better with this Unsloth. That's why we'll be using this Unsloth here. And for the quantization, we'll be doing 4-bit quantization in this project. Okay. So the Unsloth will be handling that 4-bit quantization better. That's why I'm using it, because I have a limited memory I was given by the collab, Google Colab, right? I want to make this project as cheap as possible. So that's why. So that's why we imported Unsloth, right? And we got the latest version of it. In short, that we get the latest version of it, right? So from Unsloth, we have imported libraries and other libraries also, right? So this is the fast language model. This is very important. So what this fast language model do is, okay, so its task is, we got it from Unsloth. Its task is to just load the model, right? So it's loading the model, and we are just getting the custom kernels and the memory tricks which this Unsloth is giving me, right? Unsloth is using better low division codes, right, which would be running faster on our during our training. That's why it's getting trained fast. So we are just making sure that every trick it has, every code it has, gets loaded for the training of the model, right? Then we're importing the torch, right? Because we'll be dealing with tensors, right? So that's why we need torch. And we have a SFT trainer from TRL, right? TRL is a transformer reinforcement learning, right? So I show you the reinforcement learning process, right? So the transformer reinforcement learning, we got the SFT trainer here. So there is another I got the is float 16 supported, so I'll be using that in our project to check whether the 16 is supported. 16 is just B float 16 is just the half version of B float 32, right? So if that is not supported, then we'll be using float 16 instead of B float 16. So that's why I'm importing that. And from Hugging Face, we are getting login to just log in into the Hugging Face and get the data set and all for the authentication purpose only. And from the transformer, we are getting the training arguments. This is very important to train. These arguments are very important to just train the model. Okay, so we'll be importing epochs. Okay, we'll be having a learning rate, batch size, output directory where we want to save the logs and all. So all of that will be coming from this library itself, right? So this is the training arguments we got. This from here we got the training arguments. Then there is the load data sets, right? So we'll be getting data sets, right, for the training. So we'll be getting dataset from Hugging Face. So this is how this is we used to load the dataset for a training purpose in the model during the model training, so that I can use public datasets to train my model. Okay. So and then there is a WandB. So this WandB is basically called the weights and biases, right? So what it do is, it basically a tool of ML project, right? So it will track, it will do the visualization work, charts and graph, tracking of the logs and the accuracy, the time taken to train the model and all. So and the collaboration, right? So if my whole team has been working on this project, right? So they need to see the charts and all, that how much time it took to train, what problems came and all. So that's why we are using WandB here. So to track the all the graphs and all during the training, right? So like what is the loss and all, right? If you see here these type of graphs, they can see on the WandB, right? uh, this training epoch, global step, training loss and all, that how much loss has been reduced, they will all they will see it on WandB itself. So you can see I went to the WandB and you can see what the graphs when I was training this model, right? So the loss was reducing, right? With the time, loss was reducing. This is the learning rate. Okay, this is the gradient train per gradient normalized, and this is the training per epoch, right? Epoch is the total time the model get trained on a whole data set, right? So training trained by global steps. So these are all the logs and all which is stored on WandDB, so that my team can interact with it, or I can just keep a track and see that how the training went well according to the way I wanted or not. Okay, so that's why WandDB is used. So let's move forward. So from okay, so we are getting the key Hugging Face token. We are just making sure the authentication get completed. And this is my CPU CUDA. If CUDA is available, then it's okay. So if print CUDA available, uh, we are checking the CPU and our GPU to be specific. Okay, so CUDA is available to GPU devices Tesla for T4 model. Okay, so to check whether I got the CPU or not, right? Then the model name that I will be using DeepSeek model. Okay, from Hugging Face itself, I will be getting this, and the max sequence length is 2048. So if you see the sequence length is nothing but the number of words which are generated by LLM at a time, right? So max sequence it can take as an input, and max sequence length can take as give as an output, right? So it works both way. So even if input is greater than 2048, it will cut down the input. So even if output is going beyond that, it will cut the output and show me. So it will show the output in this particular range only, right? It has some powers and limitations, like we can lose out of context if we give the less output, right? So we have to just balance it. In this project, I'm putting it as 2048, right? For the avoid the underfitting, right? And avoid the overfitting, obviously. So the logic of overfitting and underfitting is just like you went to the school, right? You there is an exam next day. You studied too much. Now you are unable to attempt a single question because there is a question that is Indian really sovereign. Then you have studied the book of Socrates and all different philosophers. One is saying that no one is sovereign. One is saying that everyone is sovereign. Everyone is free. So you are confused what to take around in the exam, whether we are sovereign or not. Okay, and the other case is you studied nothing. Okay, there was a syllabus of 3 books and you studied a half book because tokens were 2048 only. So you can't attempt question because you don't know. You will just say whatever you have been trained on and you will get 0 marks. This is the underfitting and overfitting, right? So this D type data type is none, and load in 4-bit true. So I'm loading this model in 4-bit, right? I've told you previously also. So now we'll be getting a model and tokenizer. Okay, we'll be giving a model DeepSeek and sequence length 2048, data type as none, and loading in 4-bit, and the token is HF token. Okay, HF token is the key which I have been storing here. Hugging Face key, right? So this is it. Login HF token, right? So which I will be getting for environment variable itself. So this is how we get our model and the tokenizer, right? So I did 2 times. It's okay. So now I will have to give the prompt, right? Is the system prompt that below is a task description along with the additional context provided in the input section. Your goal is to provide a well-reasoned response that effectively addresses the request. Before crafting an answer, take a moment to carefully analyze the question, and develop a clear step-by-step thought process to ensure step-by-step thought process. Okay, this is the chain of thought we are developing into. Ensure that your response is logical and accurate. Okay, be a logical and accurate response, right? Then you are a medical expert. Your task is that you are a medical expert, clinical reasoning, diagnostic, treatment planning. Answer the medical questions using your advanced knowledge. Okay, already DeepSeek, the knowledge this 8 billion parameters have, this has been trained on 8 billion parameters, right? So use that knowledge. So this is the query, right? We have to enter something here from here, right? So I'll give a query to you, and the in answer you have to think. The moment it will say think here, it will start reasoning. It will use its own brain, and here query I will give it. So it will be expecting this from me as input, and this is the reasoning he will be doing. Then I have to give a question, right? A 61-year-old woman, long history of involuntary urine loss during activities like coughing or sneezing, no leakage at night, etc. and etc. Okay, so this is the question I gave to him. Then from the fast language model, for inference, we will be putting model. Okay, then in the inputs. So in the inputs, so you can see here, we are returning tensors, right? So in this variable tensors will be stored, right? So we'll be using tokenizer. So this is the prompt style dot format. In the prompt style we'll be formatting question, okay, or this question we'll be formatting here, okay, as a query, and expecting a return of a tensor to our CPU and putting it in our inputs, okay. After that, in output we will do model.generate, that we'll ask DeepSeek that, okay, generate a response where the input ID we are getting from the tensors, okay, input from this we are getting an input ID in tensor form, because we will be putting everything in tensor form when we feed the model, right, so that it can process fast. So in attention mask I'll be using this attention mask from which I will be getting from here. Attention mask I already told you, right? uh, Here attention mask, it was the part of process, right? Masking process. Yeah, this one. So if we see here, this mask, this mask, okay, this mask is the attention mask. So what's the logic, I mean, what's the logic behind attention, why we are using it in a project in the first place, right? So typically the logic behind the attention is that attention mask is nothing but a collection of 0 and 1, right? One is the part where we have to focus on, right? So we are getting tensors, right? Everything was getting into tensors, right? Tensors. So we have to tell him that, okay, which part is important and which part is not important, right? This is a padding, right? If there is a attention part of this thing also, then I have to make a batch out of it, right? So rest of it is be given zeros, and we will tell that, okay, this you have to ignore, this is the mask, okay. So this is the attention mask concept, because in this concept we can see that, okay, if we have a small sentence, right? So if we gave a small sentence, it was a very small, I mean, can't fit into a batch, right? It was less than we expect it to be in a batch. So we give more zero zeros to it, so that in that sentence, in the tensors of that sentence, we can add zero and compensate the empty space with a zero, right? Called padding, okay. So the attention mask role is just to tell that, okay, these zeros are paddings and you have to please ignore it, because these are paddings. So this is what attention mask will be doing, and the role of mask is in our project also, right? So that's the concept behind. So let's move forward. We have attention. So we have attention mask covered, and now max new token equals 1200. Okay, so the output will be in the 1200 tokens limit, right? Use cache, yeah. You will be using cache. Okay, cache memory. Okay. Now we will be decoding our tensors, right? So For this we use batch decode function, okay, from the tokenizer. Tokenizer is here we made tokenizer, right, from the DeepSeek itself. From pre-trained we get the model and the tokenizer, and from the tokenizer itself we'll be getting the input IDs and attention mask, okay, in the tensored form. Now this tensored form need to be decoded, right, into back into the human readable form. We are get decoding it using the tokenizer itself, and we'll be getting an human readable output. But this thing is important for us. This thing is very important for us, this beginning of sentence and this end of sentence. So further, when we will train our model on some data set, then we will be telling that okay, you have to stop here, okay, you have to begin here. At that time, for this DeepSeek we need this to tell him that okay, begin and okay, close, because he knew it is the custom to do the generation and stop the generation of the reasoning, right? So after that we just did the parsing, right, of the output, because it was coming in a single line. We just wanted the think part, so that's why we just got the first iteration. So we'll be just parsing and getting the first iteration, and after that we'll be using the split function and splitting by the string, okay, answer, to get the relevant string which we want to as a output, right? See this answer. So we'll be splitting by this itself and getting the think out of it, think part out of it, think part out of it, okay, this part, this and this in the output itself from here. So let's move forward. We have a medical dataset, which is our Freedom Intelligence Model O1 SFT. We can see it in our Hugging Face itself. So if we see on the Hugging Face, we can see that okay, this dataset has three columns. One is question, one is complex chain of thought, and one is response, right? And we have a 33-year-old woman is brought to, okay, a 33-year-old woman is brought to emergency department 15 minutes, okay, like this. We have a data set, okay, like a conversation which I showed you in this itself, right, in our corpus, chat corpus, right, in supervised fine tuning. We are using supervised fine tuning only in this project, right? This is the corpus, right? This is the conversation idleness response, and we are training our GPT model into this chat supervised fine tuned model. So this is what we are doing here itself, okay. So we'll be loading using the load dataset, okay, public dataset from Hugging Face. We will be loading it. It's a English dataset, and after that we'll be splitting only the 500 out of it, because I have limited memory here, right? I'm on Google Colab, so we just want the 500 top rows to train our model, top 500 chats only. So the trust remote code, yeah, I am trusting this remote code. Okay, so after loading the dataset, we have seen the first row, right? A 33-year-old woman brought to the emergency room and all, right? I told you this was the thing written, right? So you can see we have a question here, we have a complex chain of thought here, right? And we have a response here, just like we have it here, right? Question, chain of thought, and response. These are the three things we have. And we have a EOS token, okay. This is our end of sequence token, right? We got it from tokenizer itself, which we got, okay, up there. So from the tokenizer itself we are getting end of sequence token to define that okay, when to stop. Okay, this was the thing I told you previously also, right? End of sequence, begin of sequence, start of sequence, end of sequence, right? We got it in our object as it is, right? We will be using it in our project so that we can tell her okay, now stop your reasoning. So we have a train prompt style. We'll be using it to train the model, right? So below is an instruction that describe a task paired with an input that provides further context. Write a response appropriately completes the request. Before answering, think carefully about question and create a step-by-step chain of thought. So this is important. Think carefully about the question. Okay, and describe a chain of thought to ensure a logical and accurate response. We have to be logical and accurate. Okay, the temperature, that chain of thought. You have to develop a step-by-step chain of thought before answering and fully carefully examine the question. These are the steps I'm telling him to do. Then you are a medical expert already, and knowledge in clinical reasoning, diagnostic, treatment planning. Please answer the following medical question. Okay, we have a data set here, and we have three things, right? We have a question, reasoning, and the actual response. The question, the reasoning, and the actual response. Reasoning and actual response, we have put think in it, and question we will be providing it, right? So while you're defining a function, right? Pre-process input data. In this we will be supplying our examples, right? This examples what it is. So in the form we'll be using the function down. So right now we are just making it. Inside we will be putting our medical LLM data set, right? Which we got it here. We will be putting this, right? When we're training our model. So initially we have to do this by ourselves, just making it a dictionary or so. Then after that, fine tuning dataset, medical dataset, or map pre-processed input data as true. But now it's not required. We can directly just put it in PFT, get PFT model itself. Okay, low rank adaptation. When we'll be doing low rank adaptation, then okay, it's then update, right? So after that, we'll making a text when we'll be just going through. So when we get medical dataset in here, it has three things, right? Medical dataset has three things: question, chain of thought, response. Okay, question, chain of thought, response. Question, chain of thought, and response. So we'll be extracting it from our medical dataset and putting it in input, COTS, and outputs. Okay, the whole thing, 500 things, 500 rows. Okay, after that we'll be just traversing it one by one, making it a zip file and putting it in the relevant column. So it got a zip now. Okay, each and every zip we have made, the traverse will go through one by one, right? So now we will be formatting input, COT, and chain of thought in train prompt style. This we will be putting inputs, chain of thought, and output, input, chain of thought, and output. Okay, one by one, plus end of sequence token, plus end of sequence token here, so that you can end the sequence after that. Okay, after that what happens, we'll be expecting a return of text, right? So it will be giving us a return of text, which is the which is the list which will be having result after we appended uh, it from the text. Okay, we appended text in it with what we got, right? After end of sequence, the output we got, then return text, then it will return when to the variable which will call this function. Okay, the function always returning to the variable, the calling variable. After that what we'll be doing, we'll going towards the model LoRA, so the low rank adaptation. So the logic of LoRA and QLoRA, right? So what happens is that in LoRA we don't have to train the whole model itself, right? We are not training the DeepSeek whole as a thing, right? We are just training the some parts of the DeepSeek, okay, the medical one, and after that it will be just adapt the new learning in its whole model itself, right? This is the LoRA, right? And in QLoRA what we are doing, we are quantizing the other part which should be non-affected and only training the relevant required part, right? That is a QLoRA, right? Quantized LoRA, which is the much quantized form of LoRA, right? So that's what we are doing here also. So we are just giving our model, right? Our model, and we are giving R. R, what is R here? R is the rank of LORA, right? In this PFT, this is the R of LORA. Okay, rank. The higher the rank, the more adaptability the model will have. The more learning the model can do, right? It should be not too high, not too less. Just as I told you, overfitting and underfitting, right? And this is the after the rank, giving the rank, these are the target modules. The target modules are nothing but the QKV, right, which I have showed you, QKVO. So these are the Q projection, K projection, V projection. Q is the query, my question, right? K is the key projection to enter in the database, right? So then we have V projection. V is the change in the value of the output. So the transformation which will be having in the value due to the fine tuning, right? Due to the LORA, low rank adaptation, PEFT, which will be having the transformation in O in V. Okay, the value, the output we have. So these are all the projections. So if we see, these are all the part of QK. We have seen that it's part of our attention, right? So this will combinely Q, K, and V tell me that which part of input I have given, right? I have given some input to it. Which part of input as of the data set we will have more attention. We will give more attention to which part of input we will give more attention to. It is a doctor data set, right? So accordingly we will give the attention, right? So Q, K, and V. So these are the attention part, self attention mechanism part, right? So after the QKV self attention, we will having O, right? O is the output. What output? If you see here, yeah, this one. If you see in this diagram, you can see that okay, we have Q into K, right? Matrix multiplication of Q and K, right? This one. We are doing matrix multiplication of qk, then we are scaling it, dimension thing, then we are masking it, attention mask, I told you the padding and all, right? Then we have softmax converting into probability. Then when we do the matrix multiplication, this is the O part. Okay, q into k, matrix multiplication into v, q into k into v, this will make me a O, this will give me an O. This is the O projection here. Then this is a great gate projection, right? So what this gate projection is a part of feed forward neural network, right? If you see here, yeah, so it's a part of feed forward neural network part, right? After the attention, feed forward. So feed forward, what it do, it give it to the decoder side, right? After encoder, it will give it to decoder, right? So whatever it will give to recorder will be decided by this G, right? Like how much information will be moving forward. Okay, this is gate projection. This is gate projection, right? This gate projection. Okay, so let's see. Okay, you can see, right? This is feed forward. It is giving to encoder decoder attention, right? So the part it will give, it will be decided by gate projection. And after that we have two important things like up projection and down projection. It is also a part of feed forward neural network as it is. Okay, this, it's a part of this itself. What it will do, so we have two things, right? We have up projection and down projection, right? We have up and we have down projection, right? So the up projection task, so what it will do, it will up project the training into a higher dimension, okay, to make the complex connections. Okay, complex connections it will make. After making the complex connection, this down part comes into action. It will bring down that higher dimension data to down, so that it can to the towards the lower dimension. Okay, so that it can simplify that data which will be got from getting the complex connections. So it will simplify the data, and after that, it will be it will moving forward from the feed forward to encoder decoder. Okay, so this is the logic happening here. So now we have two things, right? Low rank adaptation alpha and low rank adaptation dropout, right? What does alpha do? Alpha tells that alpha tells the scaling, right? Scaling, by scaling I mean what? By scaling I mean that okay, there are some changes, right, which will be happening after this low rank adaptation, right? So how much change that low rank adaptation will be putting on the model which was not on the original model, right? On the original model, how much changes has been applied by the low rank adaptation is the LORA alpha, and 16 is a very medium value in all the documentations basic for to fine tune a model at this low scale, just like I am fine tuning. 16 is the safest thing. And now the LORA dropout. LORA dropout, what it means? It's like during the training, how much parameters you want to drop from the LoRa layers, from the low rank adaptation layers. And now we will see that okay, why you drop, why we need to drop. I have told you the example of overfitting and underfitting, right? So you have to drop something to avoid the overfitting, to avoid the confusion, right? So that's why we are using a dropout. Right now we are just using 500 rows only, a small data set. Then why I need to drop? So that's why I put 0. Bias is none. Checkpointing Unsloth. So the checkpointing part has been allotted to the Unsloth as it is, right? Because of its advanced features, right? So checkpointing work will be done by Unsloth because if you see, checkpointing will be taking memory, right? So that efficient memory utilization will be done by Unsloth better. So I can say that okay, I have to deal with low GPU memory utilization because already my GPU is very low end, right? So and it's limited in the free version of Colab. So that's why I have been using Unsloth in this project. The main thing is this only. So that low GPU memory consumption. Okay. So now we'll be having a random state 3047. So what is this? So random state, what it do, right? It's 3047 is just a seed value, right? So it is used to control the randomness in the training process. So I mean, if you see a machine learning model, right? So in that we use randomness at many places, like to initiate some weight, right? Weights have been given. It's given random. Data has been shuffled randomly. I did the dropout here, right? And I didn't did it, but if we did the dropout, how the dropout will happen randomly, right? So random things have been happening. So every time randomness will be generated, it will be happening in the same sequence. So I can ensure that my the training results are which I am getting, right, it becomes repeatable again and again. Every time I train, the results will be repeatable. Why? Because random state is 3047, right? So it is the seed value, seeding value. So if I'm running it in future with same code and same settings, there will be more chances that the result will be same. Okay, that's why it's used here. And it will further help the future teams to just do the debugging and all, right? So that's why it's used here. So then we have RS, low rank adaptation, right? This is rank stabilized low rank adaptation, which is used to bring more stability and more performance. But we are already using the Unsloth, right? So we don't need that right now because I have low VRAM, right? So that's why the LOFTQ config. This is just used to uh, use for more efficient memory efficient training, right? So in this there will be a combining combination of LORA fine tuning, right, and the quantization. I mean loading the memory in a very low memory environment. So I'm not using it right now here, none, because to avoid the complexity, right, and I don't have computation cost. I don't want more computation cost burn because I have uh, limited VRAM with the free collab, right? So right now I'm using that only to complete this project. Okay, so So this is to just fix error which was coming during the SFT training, right? This is to fix that error, this code. Okay, unwrapped all generate. Del model unwrapped all generate. Model is unwrapped all generate. So after that, we'll be moving towards the SFT training, where the trainer is our object in which we will be storing our trained SFT trainer. So the model which we'll be using is our model which is right now having the latest data set, right? Which I want to have the latest data set, right? If you see model LoRA, right? We've done the PFT on it, right? Pre-efficient fine tuning, right? We have done it LoRA and LoRA. So after that we'll be using this model only, LoRA model. After that the tokenizer which we got at the first place up there, okay. Training dataset will be medical dataset, okay. This medical dataset, okay, we'll be using this function now. So training dataset will be this medical dataset, this one, right? So we'll be doing supervised fine tuning on this medical dataset. There will be a formatting function, pre-process input data. Yeah, this is the function which we will be using now. Pre-process input data, right? We have question, we have complex chain of thought, we response, this one, then we'll zipping it, then we are putting it, formatting in the train prompt style, then getting the output, end of sequence token, and getting the text out of it. So we'll be getting the text out of it and storing it in formatting function. Okay, after that the max sequence length is the max sequence length which we have defined up there also. And uh, and if we see the max sequence length up there, I think it's just in the step 5, right? Yeah, max sequence length is 2048 token, right? Sequence up to 2048. So this will generate the same output, okay, 2048 SFT trainer. And there is dataset num proc 1, right? How many CPU cores we are allotting? Right now, I have only one GPU, T4 on, though I will giving one only. Okay, if we are doing it on Kaggle or something, I think you can give it two, right? Kaggle is better in this aspect. So after that, we are giving some training arguments. We imported them already, right? I've told you in the starting we were importing these training arguments, right? I've told you the arguments we'll be using, right? Training transformers library of Hugging Face will be using training arguments. Now let's see these training arguments we have imported, and in this we have per device train batch size 1. So what this line means, I mean per device train batch size 1. So in each batch it will be getting only one example to learn, right? It will be trained on one example itself. It will, I did it to bring them better generalization, right? So that it doesn't cram the data, it generate the. So I got a small data set, right? Only 500 rows I've been taking. So I've done it one only, right? Only one example, so that it can it. I have the have the privilege to get more generalization, more learning sequences out of it. I can train it better, right? But in big data set, it will take more time, so I can't just put it one, right? In big data sets. So this is important. Then after that we have gradient accumulation steps, right? So what happens that, okay, there are going into batches, right? Data is going into batches, so it will gather around 8 batches. After that it will send the data. So I mean so we have to update the gradients here, right? So to update the gradients, or we can say our learning signals, right? So my model will accumulate the batches, right? So here my model will accumulate 8 batches. So my model will take 8 batches at least. So 8 batches, and after that accumulating 8 batches, then it will do the generalization part, then it will update the gradients, right? Then it will update the gradient, sorry, not generalization, do the update the general gradient part, update the gradients. So we are doing it to stabilize the training itself, so that we don't face any error. For example, we use sleep also in some examples, right? In Python examples, we use sleep 1, sleep 2, sleep for 3 seconds, sleep for 2 seconds, so that it that processing becomes smoother, right? does not overload. Just like AWS, we have a step function, right? Multiple lambda function are going, multiple processing happening. If we don't give sleep in it, it will just throw me a error. AWS will throw me a error, right? That error happened in during processing and all. So similar way, we are just making sure that eight to update the gradients, at least eight batches we need. Number of train epochs. Okay, so it will get trained once in a for on a whole data set. We are giving 500. So warm up steps are 5. Initially what happens is there is a warm up phase, right? Then after that it will gain the pace. So initially the model will be learning slowly, right, in the initial phase of training. So till how much time the model will learn initially slowly? So till 5 seconds, till 5. Okay, this is done to protect the instability during the learning, right? So that the learning happen in a good graphical way, in a linear graphical way, right? See, learning. So that's what we are controlling here. Okay. After that we have FP16. If the B float 16 mod is not supported, okay, okay, then it will return a. So if B float 16 is supported, right? If not supported, so it will give false errors. So we will be taking the FP16, right? So it will become true. If we have this, then we don't use this. If we have this, then we don't use this. This is the logic here. Then this is the BF16, right? B float 16. When we'll be using bfloat 16, when the bfloat 16 is supported by the model, right, then only we will be using it. So it will return a boolean true, then we'll be using bfloat 16. Okay, first we'll check this whether the fp16 is here or not. So if it's not supported, then we'll be using this, otherwise we'll be using this bfloat 16. So after that we'll be having logging steps. So after 10 steps, just do the logging. After every 10 step, do the logging. So this logging thing will be done by the WandB itself. So after every 10 step it will be doing logging, right? So after that we have weight decay. So this is applied to just make sure the weight remains in a particular range, right? I don't want my model to get overfitted, right? So that's why I'm using weight decay, so that the model weight doesn't grow too large with hell lot of information which it can't consume, right? Because I don't want to confuse my model, and I want my model to be simple and more generalized, which is understanding the patterns behind the data, not just cramming the whole data as such. Okay, so now we have a learning rate scheduler type linear. So okay, so we are ensuring that okay, the learning happening by the model is in a linear way, right? So initially you have seen that warm up will happen, right, for 5 seconds, 5 warm up, right? After the warm up, the learning rate will slowly linearly decrease, right? After the warm up phase, the learning rate will slowly decrease, okay, with time, when the till the time the training is completed. Okay, it's in a linear form, right? So we ensure that linearity here. Then there is seed 3407. So this is same to control the randomness, and for the future debugging I've already explained it. Okay, output directory is the outputs, right? So okay, so now we have to set up WandB, right? So I've stored the WandB token and API key here, okay, itself. And after that I'll be using WandB in it. You can easily find this in documentation, whole thing. Okay, you give a project, okay, project name, job type will be training, and anonymous will be allow. Okay, so I'll be giving this project name, okay, fine tune DeepSeek model on this on medical COT data, right? So then after that it will be showing me, okay, currently logged in as Varun Rathore AI and all, right? Then after that I'll do trainer.train. I'll be starting the SFT training of my already PEFT enabled model. Okay, PEFT enabled data fed DeepSeek model is now getting trained by Unsloth, which is 2 times faster fine tuning my model using one GPU because I only have one. Total steps will be 60. My number of examples took 500 and batches per size one, just like I said. Okay, train parameter, this, and this is main thing. See, the loss 1.93 to 1.39, 1.93 to 1.37. So what this it's doing is it's 2 times feeding the data. Okay, so the Unsloth is 2 times just giving the data to model 2 times so that my model can process that data 2 times. One is for forward, one is for backward, right? One is for forward and one is for backward, right? So 2 times it will be giving the data, and due to its efficient PEFT techniques, right? It is training it is doing the fine tuning much faster. Okay, for this type of model, so that's why I chose the this uh, Unsloth. Okay, the sloth means slow, un means none, so cancelling out each other and making it fast. So jokes apart, but this is the reason I chose is Unsloth. Okay, so because of its better algorithm, better low code, better low level codes, yeah, which will be running fast on the GPU, consuming less memory, processing better. Okay, after that we'll be doing WandB finish to see all the parameters. Okay, training went well, learning rate was linear, and training loss decreased with time. Okay, the epochs 0.96, training steps per second 0.52, samples 413, loss. Now let's move forward and see. Okay, uh, now we'll test our newly fine-tuned model, right? We'll give a question like we did before. Okay, 61-year-old woman, long history of involuntary urine and all. It's the same question, right? Then we have fast language model for inference. We're using fast language model, okay, for inference. Then now we are putting our model LoRA, okay, fine-tuned model. We're using this model. Then the tokenizer will be getting our tensors, right, storing in CPU. After that formatting question, prompt style dot format question. Okay, prompt style is up there in I think it's up there. Prompt style is up there, yeah, I think step 5 or 6, I think step 6, yeah, prompt style. Below the task will be entering question here and this thing, right? So now our model is fine tuned, right? I told him well reasoned response I want, step by step thought process. Here if you see, okay, so I'm trying to figure out what crime history would show for a 61-year-old woman. Okay, then the output is this, right? The crime history for this 61-year-old revealed that increased residual interest. Okay, this was the response, right? Now see what response now we will get after we feed this into our prompt style and use this model for that. So doing this, input id which we got from here, tensors and attention mask, max new token, max 1200 words, cache we'll be using. After that we'll be decoding. After that we'll be parsing to get the output. Yeah, this see this. All right, let's take a look at the scenario. All right, let's look at a scenario. Okay, so it will be taking a chain of thought, right? I told, right, sequence, whatever the I told him, it's doing exactly that, right? That step by step process. We have got a 559-year-old woman who's been feeling pretty unwell. He's got high fever, chills, night sweats, feeling exhausted. Sounds like picture of endocarditis. Recently, just he reached a conclusion, right? And after that, which is an explain that disease, okay, just like the way I want it to do, right? Just like I was giving him a feeling, right, in my prompt style, right? So it's connected both prompt style and this question well. After that, it has gave me better answer. So it is the reasoning which he has gone through, and from this reasoning, this better reasoning, it has gave me a better final response. What is that better final response? The most likely predisposing factor of a 59-year-old condition, the question has been included. Given the presence of 12 vegetation on the aortic valve, the specific type of bacteria identified gram positive it suggests infection is likely due to the streptococcus species. Okay, so this output is so much better than the previous one, which was a mess. Okay, because it has now been trained on a data which is specific to solve these kind of diseases and other stuff, and it's just the 500 rows we have took. Imagine more rows if I have took, how much better it would be. But in the end, is fine tuning just a wheel, like balancing wheel. Like sometimes you have a lot of data and you have a model which is just too much less powerful to handle that, and just cram all things and become confused. So you have to balance the amount of data with your model, right? So this is in the end the feeling of fine tuning, right? You have to balance the things, each and every concept you have to just imagine, each and every concept you have to make a plan out of it, then you balance the things accordingly, then you would fine tune, right? And I think much more inventions are being done in this field only, right? Because in the end, what you are feeding the model, he will just uh, think like that itself, right? So that's all I think from my side. So this is all from my side. I have trained a model show a response, and I have a very nice day ahead. And it is added to my GitHub repository. If you want, you can check it out, or this IPYNB file, right? Thank you, and have a very nice day ahead. Thank you.